Okay, here we are on the last problem. We're almost done. Okay, and this is the real reason for doing this entire quiz and this entire section is to be able to carry out a problem like this one. Okay, and again, what's the big picture? The big picture is that somebody is giving you a test tube. It has cells in it. You don't know what the concentration is. However, because of the math that we have just learned, we can actually calculate what that concentration is, okay? And so the question reads, it says, you're told that you have a sample with somewhere between 2.5 times 10 to the fifth and 2.5 times 10 to the sixth cells per milliliter. In other words, somebody's giving it to you, some researcher, and they go, look, I don't know what the concentration is here. The only thing that I can tell you is that the OCD, the original cell density, is somewhere in between these two. That's my guess, okay? So we're giving you a guess, and that gives you a little bit of help. Now it says device a complete but efficient, that means we're not gonna waste any plates, dilution scheme that will ensure getting a countable plate. What's a countable plate? A countable plate, again, is a plate between 30 and 300 cells that will allow you to backwards calculate the original cell density, okay? So what are we gonna use? We're gonna use this equation right here, okay? Again, we're gonna paste it down here, and I'm gonna make it a little bit shorter. Instead of volume plate, I'm gonna call it VP, because, well, I like it as in short. Instead of dilution factor, I'm going to use DF. Okay. So we have a dilution factor and we have a volume plated. Okay. So the original cell density is equal to number of colony forming units divided by volume plated times dilution factor. And what we're trying to find here is a dilution factor that will allow us to calculate when we will achieve a countable plate. So we have to solve for that dilution factor, okay? So I'm gonna go ahead and use my equation writer, and I'm gonna say, okay, so OCD is equal to number of colony forming units, CFU, and we're gonna divide that by volume plated times the dilution factor. And I need to know what my dilution factor is. So I'm going to solve for it. So I'm going to find my little arrows here. Okay. And this implies that my dilution factor, again, I'm solving this algebraically. Okay. I'm solving this algebraically. So I'm going to multiply both sides by dilution factor, and then I'm going to divide by OCD. When I do that, what do I end up with? I end up with CFUs in the numerator, and then in the denominator, I have OCD times volume plate. That's what I end up with. So I multiply both sides by dilution factor. The dilution factor cancels on the right denominator. It ends up in the left numerator. Okay. Like leaves me with CFU divided by VP, and then I divide both sides by OCD. That gets rid of it on the left side, and I end up with it on the right side. So this is a formula that we have to solve, and we have to solve it exactly twice, okay? And the reason for that, really there's 4 permutations. If you look at it, we have 2 CFUs. Why 2 CFUs? Because we're trying to reach a countable plate, which again is between 30 and 300, okay? So you have 1 colony forming unit set of 30 and 1 colony forming set of 300. And then what else? Well, we also have 2 OCDs. They're right here. Here's one is 2.5 times 10 to the 5th, and the other one is 2.5 times 10 to the 8th, because we have 2 guesses, okay? We could do all 4 calculations. We're not going to, because from experience, I know that we only have to do 2. We just have to choose wisely, okay? So what we're going to do is we're going to follow this equation right here, this one right here. And what I need to tell you is that in order to find every possibility, you have to do that one with high OCD, low CFU, and the other one with low OCD, high CFU. So I'll show you what that means. So remember, we're following this equation right here, this one right here. We'll put it in red so nobody can miss it. And we have to choose, let's see, high OCD. Let's see what I'm seeing here. Yeah, that'll work. High OCD, low CFU. Okay, that's one permutation I have to do. And the second permutation I have to do is low CFU, low OCD, high CFU. Okay. You can do all four if you wanted to, but it's going to be a waste of time because I know that this happens to work really well. So here we're going to do our equation. And you go ahead and insert. And I'm going to say that my dilution factor is equal to what? Well, I have CFUs in the top, and here I'm supposed to go low CFU. Okay. What's low CFU? Remember, 30 to 300. 30 colonies in a plate is low colony forming units. 300 is high. Okay. So if I'm going to go with low CFU, I want a countable plate with only 30. So we go 3.0 times 10 times 10 to the first CFU, because 3 times 10 to the first is 30. That's my low CFU. Okay. If I was going to do the other calculation, let's do the other calculation. Put it down here. Okay. This one is high CFU. So if this is 30, then this one should be 300. So it's going to be 3.0 times 10 to the second. There, that's done. Now we have to do original cell density. What kind of an original cell density? In the first one, it has to be high. Which was the high between these two? Well, 10 to the 8th is higher than 10 to the 5th. So that's my high. So right here, at high OCD, I'm going to put 2.5 times 10 to the times 10 to the 8th, because that's my high, and that's going to be CFUs per milliliter. Okay, and then what else? We have to multiply. We have to multiply by volume plated. Okay, it turns out that anytime, unless you're told otherwise, the volume plated is always 1/10 of a milliliter. Always 1/10. So we always put in for the volume plated 10 to a negative first mLs. That's just a standard amount. Okay, let's do the bottom part. On the bottom part, we have to do OCD. What kind of an OCD? A low OCD, which is a low one, this one right here. So here we're going to go 2.5 times 10 to the what? To the 5th, because that's our low range guess. And then we're going to multiply by the volume plated. The author has not told us how much, so we have to conclude that it's going to be 10 to the negative first mLs. In other words, 1/10 of an ml. There it is. Okay. Now, if you notice, colony forming units in the numerator. Whoops. Let's see if I can do this. Colony forming unit, it doesn't want to do it. There we go. Colony forming units in the numerator cancels colony forming units in the denominator. And that lets me notice that I forgot to put units on here. The CFUs per milliliter. Okay, so that one cancels too. And then we also notice that the milliliters in the denominator of the denominator cancels the milliliters in the numerator of the denominator. And we end up with a pure number, and the dilution factor is a pure number. It has no units. So that means that we're doing something right. Okay? All right, over here, there's going to be a quotient again. The top remains the same. There it is. And the denominator is going to be 2.5 times 10 to the what? Well, that's to the 8th, and that's to the negative first. If the bases are the same, we add the exponents. So 8 minus 1 is 7. So it's going to be a 10 to the 7th. And then over here, we're going to do the same quotient. This is going to be 3 times 10 to the 2nd. There he goes. And we have 2.5 times 10 to the what? 5 minus 1, because if we're multiplying, we add the exponents. This is a 5 plus a negative 1. 5 minus 1 is 4. So it's going to be a 4. Okay. Now what? Well, it turns out that 3 divided by 2.5 is suspiciously close to 1. So we don't care about that one. The reason we don't care is because in the dilution factor, we only care about magnitudes. In other words, powers of 10. So 3 divided by 2.5 being very close to 1, we're not going to care. We only care about the exponent. If you don't like that answer, another way of doing it is like this. Take your 3 divided by 2.5. That gives you 1.2. If you were to do that in exponential, that would be 10 to the 0. In other words, nothing changed. But if you take the numerator and divide it by the denominator, and you get 5 or greater, then we say that that's close enough to 10 to push it to the next magnitude. And we would call that a 10 to the first. Okay? So here we have 3 divided by 2.5. That's 1.2. That's very close to 10 to the 0, so we're not going to worry about it. And so here, this is going to be 10 to the 1 minus 7, which is going to be a minus 6. And then over here, this is going to, oh, sorry about that. There we go. This is going to be equal to a 10 to 2 minus 4. It's going to be a minus 2. So it's going to be a minus 2. So there is our, there's our range. Here's our highest dilution right there. And there's our lowest dilution right there. So that means what? That means that the set of dilutions that you need are starting at this one. Oops. Let me get rid of some space here. There we go. Starting at this one, and it's going to be 10 to the negative second, 10 to the negative third, 10 to the negative fourth, 10 to the negative fifth, and 10 to the negative 6. And I'll go ahead and make those superscripts. Okay, go ahead and center them. So there's my lower bound, there's my upper bound. So that means I would have to do a dilution with my sample. I'd have to dilute by 100, by 1,000, by 10,000, by 100,000, and by 1,000,000. Okay. And then I would use how 1, 2, 3, 4, 5 plates. And we do it redundantly. We multiply times 2. We plate 2 plates for each one. So it's 5 times 2. So I would end up using a total of 10 plates. And that is guaranteed to give me a countable plate between 30 and 300. Okay. So that's it. That's the most complicated one. Once we find a countable plate, now you can use one of these formulas to calculate what the original cell density is. And that's all there is to it. I hope this made a little bit of sense to you. And thank you for your time and your patience.